Jupiter, the giant of our solar system, boasts a moon system that's as varied as it is fascinating. In stark contrast to Earth's solitary, unchanging moon, Jupiter's moons span a dramatic range of landscapes. While our moon is a familiar cold and barren presence, Jupiter's moons feature fiery volcanoes, spewing lava into space alongside moons of icy oceans, hidden beneath thick ice that might just harbour life. Here, serene frozen worlds coexist with moons transformed by intense geological activity, and with the Jupiter system home to a multitude of captured moons, it's no surprise Jupiter is called a miniature solar system. But how did it end up like this? And why are the moons of Jupiter so contrasting? The story of Jupiter's moons begins 4.5 billion years ago in the swirling gas and dust surrounding the young planet. As Jupiter formed from this circumplanetary disk, its powerful gravity started to shape the material around it, setting the stage for its moons. Close to Jupiter, the intense heat prevented the formation of ice, leading to the creation of rocky moons like Io, a volcanically active inferno. Further out, where temperatures were cooler, ice could form, giving birth to moons with icy surfaces, such as Europa, Ganymede and Callisto. Europa is covered in a thick layer of water ice, whilst Ganymede, the largest moon in the solar system, features a mix of rock and ice. Callisto, the furthest away from Jupiter, has an icy shell that hides a heavily cratered surface, indicating a tumultuous history that has not been removed by geological activity. Jupiter's moons display a wide range of landscapes crafted by powerful natural forces, primarily tidal heating, a phenomenon caused by the gravitational pull Jupiter exerts on its moons. Take Io, for instance. It's the most volcanically active body in our solar system. The constant gravitational tug from Jupiter and its surrounding moons Europa and Ganymede stretches and flexes Io, generating immense internal heat. This heat powers Io's many volcanoes, some of which have been known to launch volcanic material 500 kilometers into space. Europa, while less visibly active, also experiences tidal heating. Beneath its 15-kilometer thick icy crust, scientists believe there's a vast 100-kilometer deep subsurface ocean, kept liquid by tidal forces. Also, the flexing of Europa's ice shell causes cracks on the surface, allowing the liquid water to occasionally erupt as plumes. This activity, combined with strong evidence of cryovolcanism, makes Europa a top candidate in our search for extraterrestrial life. The varying geological features of Jupiter's moons are further influenced by orbital resonance. Io, Europa and Ganymede are in a gravitationally synchronized pattern. For every 4 orbits Io makes, Europa makes 2, with Ganymede making 1, and this amplifies their gravitational interactions, increasing tidal effects, and it's a critical factor in maintaining tidal heating. While Io bears the intense impact of this with its visible volcanic fury, Ganymede also experiences some tidal heating that is more subtle. As the largest moon in the solar system, Ganymede has a unique magnetic field, likely generated by a partially liquid iron or iron sulfide core that remains molten due to tidal heating. This tidal heating, combined with Ganymede's composition of rock and ice, contributes to a surface that displays both ancient, heavily cratered regions and younger, less cratered areas. These features reflect complex geological processes driven by gravity and the effects tidal heating has on the moon's surface over time. In contrast, Callisto's heavily cratered surface, which suggests a history of many impact events, reveals a quiet geological past due to minimal tidal heating compared to its more active siblings, allowing the craters to remain largely unchanged. The lack of significant internal activity has preserved Callisto's craters, offering a pristine snapshot of the early solar system, and although there is some evidence suggesting the presence of a subsurface ocean, the absence of internal tidal heating keeps Callisto geologically stable and largely dormant. Beyond these 4 moons, Jupiter's smaller moons represent an intriguing story. Many were not formed from the circumplanetary disk but were captured from elsewhere. These irregular moons, including Himalaya, Elara, Pasiphae and Sinai, follow highly eccentric orbits, suggesting they were captured by Jupiter's gravity long after the planet formed. Some of these moons belong to collisional families, groups of moons with similar orbits that are believed to be fragments of larger bodies shattered by ancient impacts. Many of these smaller moons also have retrograde orbits, meaning they orbit in the opposite direction to Jupiter's rotation. This feature reinforces the idea that they are captured objects or remnants of bodies that suffered violent ends. Their presence underscores Jupiter's role as a gravitational powerhouse, reshaping everything that comes near. While Io, Europa, Ganymede and Callisto are large and likely formed from the same disk of material that surrounded Jupiter during its formation, many of the planet's other moons have different origins. These smaller moons, often captured asteroids or fragments from ancient collisions, reveal the diverse and intricate effects of Jupiter's influence. Together, these moons create a complex system that reflects the immense gravitational pulling power of Jupiter and the profound impact it had in shaping its miniature solar system.